what I'll be talking about is approximating eddy distance in near linear time. And the approximation is constant, so not to keep it a surprise. And this is joint work with Negev Shekel-Nosatsky, who is a student at Columbia University. And I'll be able to cover only a few bits of our algorithm, but a full paper is available on arXiv, and please do take a look after we talk. So okay, so let me start. I'm sure most of you are familiar with eddy distance. It is a basic it's a basic distance between strings, and the point of it is that it measures misalignments between strings, as opposed to, let's say, Hamming distance, which is just the number of different characters or different coordinates. Right. So here is an example. For example, two words, banana and ananas. So here the eddy distance is 2, because we can just delete a letter B from here and then insert a letter S. This is 2 insertions and deletions that we can do to transform one word into the other. Okay, so this is a standard, the standard distance, defined many decades ago, and has many applications in areas such as, for example, bioinformatics, where you think about, computing this distance between, let's say, genetic codes of, the actual, DNAs of these fruits, let's say, or natural language processing. And somehow it corresponds to, more errors that can appear in these applications where, let's say, characters are inserted or deleted. Okay, and I'll denote it ed is subscript n to denote n for the length of the strings. Okay, and the alphabet in general will be sigma. It won't really be super important for us what alphabet it is, and think about it, really will be for any alphabet. Okay, so this is classic, and the solution of it is also another classic example of a standard technique that we teach in Introduction to Algorithms classes. I'm going to teach it probably in about 4 weeks from now. It's an example of dynamic programming, and we can solve it in quadratic time. So if strings are of length n, we can solve it in n squared times. As you can see, that this is close to 50 years old result. And what you do, you basically build a table and a two-dimensional array, and there is some kind of recursive formula to fill it out. This is the second formula. The first, and this is the significance. This first equation is the significance of this formula. Okay, and you can just fill this out because it's a local computation that you can just compute by iterating through all the entries of this two-dimensional array, fill out with numbers, and in this bottom right corner, you'll read off the answer, the eddy distance. And actually, from this table, you can read off more. You can read off, in a sense, what is the shortest path? What is the path along this array that gave you this number 2? And, looking at this path, you can recover, basically what actual insertions, deletions have been done, or, what characters from ananas have been transformed into characters from this other word, banana. Okay, so this is, this is very, very classic algorithm. So, and have quadratic time algorithm, so what's the issue? Well, especially nowadays, these strings are actually long. You can imagine, hundreds or thousands or more, and quadratic is just not good enough. Okay, and this is not really something that is this decade, an issue of this decade. This has been an issue of many decades already, and always wanted an algorithm that runs even faster than quadratic. So it has been a question that has a long tradition now. But more at a high level, the real question here, and eddy distance is an example of it, is dynamic programming is typically something that gives us polynomial time algorithms like quadratic this time. And a generic question is, okay, can we speed up dynamic programming problems in general? Can we get to something which is much closer to near linear, something like linear in the input size? Okay, and eddy distance is like the prime example for studying this kind of questions. Okay, so what happened for computing eddy distance? How much, did the community succeed at improving quadratic time? Well, there is an algorithm from 80s by Maciek Patterson, which improves it by log squared n factor. Okay, and pretty much that's it for computing at a distance, at least in general worst case. Yeah, there has been lots of, there has been lots of our work in trying to improve this algorithm in special cases. Let's say, for example, when eddy distance is known to be small already, or some average case or smooth case, think about some kind of random or pseudo-random kind of models of the input. As you can see, has been lots of work for decades, including in recent years. But the kind of the basic question of worst case, in general, can we improve it? Nowadays, it's not believed to be the case. In particular, there is a result that says that the quadratic time is likely the best possible. And by likely, I mean it is holds under, if you believe the strong exponential time hypothesis, or even stronger hypothesis. This is really kind of, this kind of statement is really one of the, jewels produced by the kind of modern area of fine-grained complexity. This is what this FGC stands for. In fact, this was kind of the first paper, the Bacchus Indic 15, but they proved this. And in fact, later papers, proved that even under even more plausible hypothesis, one should not expect to improve over quadratic time algorithm, even by more than, a bunch of polylogarithmic factors. Okay, so, it's natural to say, just like, I guess, past century, we were saying, well, many NP-hard problems, we don't hope to, to do anything better in the worst case, what can we do? What can we do? We still need to solve them kind of fast. Can we do it approximately? So, we can ask the same questions here. Can we approximate the distance in time which is much closer to linear, or at least sub-quadratic? Okay, so this question has been studied. I mean, in a sense, even before the conjectural hardness result. In fact, most of the progress on the problem, or first generation of progress kind of on this approximating eddy distance has been done basically in the first decade of 2000s. Kind of the end result of that line of work was to get polylogarithmic approximation in time which is close to linear. Right? This is the exact dependence or trade-off between time and the approximation. But then basically very recently there has been kind of major breakthrough. It's like, this is what I really call breakthrough, where they obtain the constant factor in strictly subquadratic time. First, there was these two results that were roughly the same time. One was the quantum time algorithm, and another was classical time. This is by the classical algorithm was by Chakraborty, Das, Goldenberg, Koucky, and Sachs. Okay, in 2018, won Best Paper Award. But of course, natural question is, okay, we got constant factor approximation. Can we do, in n to 1.6 time roughly? Can we do it better? Can we do it close to linear time? There has been some progress, and there are basically two follow-up papers that appeared this year that obtain constant factor approximation in near linear time, but there is an additional additive approximation. Okay, so for every fixed target epsilon, from the time, if you want to obtain time, which is n to 1 plus epsilon, the approximation is also some fixed function of epsilon, but the additive approximation is n to something which is close to 1, and how close to 1 depends on epsilon. Okay, so in a sense, it's put differently, it is only good to it's an algorithm that works only in the case of, gives this only holds for the case when the eddy distance is already very, very close to being maximal, right? Basically very close to being linear n. Okay, but when it is a little bit less than this function, then it doesn't say anything in that case, and we still don't know how to get constant factor approximation near linear time. Okay, or at least we didn't know until we started working on this problem. So this is our main result, that we can compute this eddy distance between two strings of length n in constant approximation. in time which is nonlinear, n1 plus epsilon. So this is the result. I'll talk about this. I mean, as much as I can. There are way too many details to cover in an hour, but I'll try to give you some glimpses of what's happening. To do that, I will start describing kind of a generic approach, which is common to the past results. Past results would give constant factor approximation, and then show how we use some idea, some of this setup plus our ideas to get this result. Okay, and I think this is a good time for me to pause for a few seconds, maybe to parse or to ask if there are questions, because from now on I'll be talking about algorithms, and it will get perhaps a little bit more technical and specific. Are there questions so far about kind of setup, algorithm?
So to the audience, if you have any questions, just raise your hand and we can unmute you.
Yes, I know this is like, very short introduction before we get into the technical things. And, for two reasons is, I feel like this is like a very basic problem. There is, most people know what it is about. Like I see through the list here, and, many people worked on related problems probably more than I did here. And so I believe you know what the problem is about. And, this is reason one to kind of have such a short introduction. Reason number two is that there are lots of, I want to give you as many ideas from our paper as possible. In the time that we have.
I have a small question, but I don't know if you covered that already, but you mentioned that with the dynamic programming approach, you can also get basically how this is achieved, or this distance is achieved. With your result, do you get the same? Do you also get a witness of the distance you get?
Good question. I'm sure that yes, but sorry, I am slightly. First of all, I think there is a result, and sorry, I don't remember all the offers. Sorry, I won't say any of them. So there is a paper which basically says that if you can estimate the distance in time, something like n1 plus epsilon, with constant approximation, then you can actually recover the optimal alignment with another factor loss in n1 plus epsilon and another loss in the approximation. Okay, so being able to compute the distance is enough for, you plug it in as a black box in some other algorithm that manages to get the alignment. Okay, so this is one. Our algorithm, at least in our paper, is, we did not look at the question of getting the alignment kind of directly from our algorithm.
Thanks.
So, well, I believe it should be doable. Okay, so let me continue. All right, so let me talk about kind of the approach setup, and again, feel free to ask me questions. Now it becomes kind of more serious kind of. All right, so the approach setup. So first of all, you think about this as kind of some kind of characterization of eddy distance that will be useful for us later on. And one thing is that eddy distance is the same as finding an optimal alignment between characters of x and y, right? So think about this as once you do the modification of one word into the other word, then some characters remain, and this optimal alignment says that this character that was maybe the first A in banana matches to the first A in ananas, right? So this is what this alignment means, and this is roughly how it looks like, right? So this is two strings x and y. I'm just showing selectively a few letters, let's say, from them. These red double arrows are the alignments, right? What character corresponds to what character from x to y. So this means that this A, once we do these modifications, if you trace where this letter A goes to, right, it will end up this A in the string y, right? And there are bottom things because some character like these double A's will be deleted from X, so they'll match to bottom basically, right? Which will correspond to deletions. Okay, so right. So this is, so okay. Part one. Part two is that what the prior approaches and we will be doing is looking at substrings, right? And think about this is, it's a kind of foundations of doing something iteratively, right? Where we do something for shorter strings and then do it for longer, for shorter substrings of x and y, and then for longer substrings of x and y, and so forth, until we get to the entire strings x and y. Okay, so but for now, think about this kind of just one step of this partitioning. So we'll be looking at substrings, and will be of certain length w, right? We'll call them capital Xi and capital Yj, corresponding to substrings of x, corresponding to substrings of y, starting at position I or j correspondingly. Okay, with blue rectangles. There are length w. Think of w as some parameter. It's kind of polynomial in n, and if you want it to be a little bit more specific, think of it as being something like n to 1 minus epsilon, right? We kind of reduce the problem from length n to length n to 1 minus epsilon. Okay. Okay, so here is a fact, and this is in a sense a fact that allows us to think about these substrings, namely the following: that if we think about it now, edit distance on these substrings, right? So x is is composed of all these xi's kind of in order, and y is composed of all these substrings yj in order. And on these substrings, when we compare two substrings, we use the edit distance on them, right? Now of length w, right? So xi and this y pi I, right? This is the corresponding substring in y. Now, these are length w substrings, so we'll think about them as, computing edit distance of length w, on length w substrings. Okay, so now if we minimize over all alignments between strings x and y, right, compute what is the cost of these alignments. Now, since our these length w substrings, we have to normalize by w. Then this is a constant factor approximation to the edit distance between x and y. Okay, so in a sense, what we've done, we've taken a problem which is hard and make it harder. Namely, now we don't compute just edit distance between, it's like we're computing edit distance where the alphabet now is consists of these xi's, which has a metric on itself, kind of, right, which is edit distance. This is, but this is kind of formally what we have. Okay, so this is somehow kind of suggests to us like, well, if we somehow reduce the problem to computing edit distance between substrings. Okay, I mean, we still have to find this alignment, but let's hold on, right? Let's see why this should help before. First of all, okay. So now, the goal can be restated as finding the near optimal matching pi between substrings of x, substrings of y, and when kind of computing this minimal alignment, we'll need to compute the distance between xi and these xi's and yj's. And for this, we'll say that we have some kind of oracle that computes us edit distance of length w between both things, right? And the question is, think about this, how many calls do we need to do? How many times do we need to compute edit distance between a little bit shorter substrings? Okay, so this is the goal. So okay, so let's discuss this, right? And this is basically along the lines of the ideas that we're introducing these papers with constant, first papers that gave constant factor approximation for edit distance in sub-quadratic time. So why should this help, right? So let's go through kind of a few steps, right? So first kind of naive thing to do is to say, well, we have substrings x and y. Let's just compute all possible pairs, right? So there are n substrings xi, for all starting positions I, n substrings yj for all starting positions j, and there are n squared pairs, for which we compute edit distance. This is n squared calls to this computing edit distance. Now, what is the best thing we know how to do for computing edit distance for strings of length w? Well, the quadratic time algorithm w squared. So get time which is at least n squared w squared. Okay, I'm saying at least because this is just computing the distances between these xi's and yj's. We also need to include the time for finding the actual optimal alignment, but we'll get there, right? Let's just really think about how many calls we need to edit distance and ignore for now finding the optimal alignment. Okay, so idea 0 is that, well, taking substrings should help us somehow, right? Well, and the idea is that it should be enough to consider starting positions which are multiple of W, right? Since we're considering substrings of length W, I mean, x1 and x2 are almost the same thing. If from the perspective of edit distance, they're very close to each other. And so kind of we shouldn't be really considering both of them. They're almost redundant. So, we should take the substrings of X, which are non-overlapping, right, but cover X. So, namely take all these which are starting at multiples of W, right? Okay. So for X, let's say, we can do the same for Y. But here's one issue is that, well, now if we are to find kind of optimal alignment between, X1, let's say these substrings which start at multiples of W and try to match them here, then it's not enough precision in a sense, right? Like our optimal alignment might be matching this X1 to somewhere, let's say, in the middle of this substring, right, and this XW to somewhere a little bit to the left here and so forth. So we definitely the optimal alignment might require that at least in Y we consider all possible substrings. Okay, so formally, when we look for every I, even which is a W multiple, then the corresponding alignment is not necessarily a W multiple. Okay, but what we can do is we'll say, well, for a distance it's okay to consider strings which are kind of nearby in some sense. So maybe we just discretize the starting positions in Y a little bit more, finely. Let's say we consider rounding J's to delta W multiples. Okay, think about delta as being very small constant. Okay, so basically we'll consider multiples of W starting positions in Y, but also a little bit shifted, right? This green starts, which is here and here and here, as well as this purple starts, right, which is here and here and here. This would roughly correspond to delta equals to 1/3. Okay, and you can do this, right? And this means that again, this is not a multiple, but you can round this to the closest multiple of delta W. This introduces some additive error. Okay, just because the alignment has to have particular form. With rounding, each rounding adds some error. Overall you can compute that this roughly adds additive delta N. Okay, so I mean, we have additive error. That's a little bit bad, but let's say that this is okay, right? For delta sufficiently small, that's fine. How many calls do we have? Well, again, for constant delta, we still have roughly how many substrings X we consider N by W. How many strings of Y do we consider N by W, times some function of delta. Let's say that's a constant. We still have at least N by W squared pairs of substrings for which we want to compute this edit distance on shorter strings. Okay, so again, if you don't have anything better for shorter substrings, still have W squared time, then the time still remains N squared. So we still haven't made any progress. Okay, at least it's not much worse, but we didn't make any progress. Okay, and this is why I call this idea 0. Okay, here's where the real ideas come. Okay, so idea 1 is the following: that we can use triangle inequality on the edit distance on strings of length W, right? So this is very cool. This is, in a sense, we're using something a bit more specific about edit distance, but, well, it is a distance, right? It satisfies triangle inequality, and we can do deductions about this edit distance of length W about pairs of substrings which we don't compute directly. In particular, imagine that some xi, let's say x1, is close, let's say x1 is close to all the substrings here in X. This y1 is close to all the other substrings in Y. And x1 and y1 are also close. Well, by triangle inequality, all the substrings between themselves are close. Okay, maybe after some factor 2 loss. But this means that, in particular, if x1 is, let's say, close to m substrings of x and yj is close to m substrings of y, then instead of comparing, all pairs, which would roughly be m squared, we have to do just 2m calls to computing eddy distance. And for the rest, we just can deduce the distance or an upper bound on the distance without explicitly taking a call to eddy distance, this EDW. Okay, so this is idea one. This was enough for quantum algorithm, but not for the standard model. So idea number two is the following. And again, a little bit kind of related to eddy distance, that, or specific to eddy distance, is that now if we have, let's say string xw, right, which starts at this position and it matches somewhere here, kind of, right, very, somewhere at this position, right? If we consider the next substring of x, assuming that there is not too many errors happening kind of around here, then this one should be matching roughly in the proportionate start position, right? Or formally, if the IW start position matches to some position j, then most likely when we look at the next substring of x, it will start basically at j plus w less. It should be plus minus the local error kind of, right? But assuming it's kind of distributed relatively uniformly, we have some kind of prediction of where should be the right match in a sense. So this means that when we're considering this xi starting this position, we don't need to compare to many other substrings in y, or like all of them, right? But just in a very localized manner. Okay, so this is idea two. And this breakthrough result from 2018, what we showed is that using these two ideas, basically, you can reduce the number of recursive calls to eddy distance w to be only n by w to 1.5. Remember this, whatever we had on previous slide was quadratic kind of, which kind. Here it's reduced to power 1.5. Total time becomes n by w to 1.5. This is how many calls, recursive calls to the EDW, to computing eddy distance on shorter strings we need to do. Each of them takes, let's say, if we use just standard exact eddy distance algorithm for each of them, right, it takes w squared time. Plus we have some time which corresponds to finding the actual pi. Okay, but remember that we're considering the multiples of w, so the number of substrings that we're really considering is something like n divided by w. So some modification of standard dynamic programming on any distance will basically be sufficient. And this constant is really a 2, but I'm just putting it a constant because it doesn't matter too much what that constant is, because n is we can take w to be sufficiently close to n, but we get some kind of improvement. Okay, and of course, you can say like, well, now we can do this recursively, in particular for strings of length w, instead of doing this kind of standard exact one, we replace our approximation algorithm. So let's say w to 1.5 if recursing and so forth. Okay, but doesn't quite give the n to 1.5 algorithm, in particular because of the second part, but close to it. Okay, and the recent papers that got the near linear time for additive approximation, they show that you can reduce the number these calls to eddy distance on shorter strings to be only near linear in the number of substrings that we care about, basically n by w to power 1 plus epsilon. But there is an extra error term, right? Remember that there is already an additive error term because of rounding the j's here. Okay, so that's part one, but there is kind of more sources of additive approximation. In particular, that if we, if we're really okay with additive approximation, then we don't really need to find all the right matches, right? So there is some kind of optimal alignment. We don't need to identify all the pairs of substring of x versus substring of y, which are members of the optimal alignment, but we can we can miss a fraction of them. Okay, and this will add to the error, but that's okay if we allow additive error. Okay, so this is kind of a super high level overview of the prior work on constant factor approximation algorithms. And now I'll describe basically our algorithm, which has the same framework, but and you'll see some traces of idea 1 and idea 2 somewhere, and I'll try to highlight those. But yeah, I just want to set up what we're talking about. Are there any questions so far? If not, let me talk about something new. All right, so here's our approach. And this is the high level, right? So, on the previous slide, I kind of suggested some kind of, recursion that, we have long substrings and we somehow recursively try to compute, for which we computed the distance on shorter substrings and for which, maybe we can use kind of recursively the algorithm. Think about this, what's happening on this slide is not the recursive version, but kind of the bottom-up version, right? As in we kind of do first things for short strings, and then from whatever we got for short strings, we do for longer strings and so forth. So more formally, think about we iterate kind of, this is the high-level loop of the algorithm. We iterate over lengths W, which are 1. This is just characters, then length n to epsilon and to 2 epsilon up to n. Right? Note that this is constant number of iterations. For each of them, we build a distance oracle. It's a data structure, which is a distance oracle. We call it dw. For the entire metric, calligraphic IW, where this is all the substrings. So these are all the xi's and yj's of length W. And so we have a metric which is on all substrings of x and all substrings of y. And the metric between them is the eddy distance. Okay, so it's a metric on 2n points in a sense, with some distance. We build a distance oracle on them. Right? I'll describe later how we built it, right? But that's the point. To build a distance oracle, which is a data structure. Okay. And the algorithm will basically say like, well, first we build the data structure for substrings of length 1. Well, substrings of length 1 are just characters. What is the eddy distance on characters? Like, well, it is exactly the same as Hamming distance on our alphabet sigma. So this is just Hamming distance on our alphabet sigma. So this is hashing basically. You can think. So given this triangle, right, this green triangle, we build a darker triangle, right, which is distance data structure, which is a distance oracle on substrings of length of n to the epsilon, and so forth, right? And until we get a right data structure for all substrings of length n, right? Which means that in particular it includes x1 and y1, which are of length n, which are exactly equal to x and y, and this will be the distance oracle, which will approximate the eddy distance. So therefore this will be the output. And the formal guarantees that we want for this oracle, informal is not all details written out, but this is what we roughly expect from this distance oracle dw. Okay, but for any two substrings I and j, not that, we usually think about them as being, I comes from string x, j comes from string y, but you can also think about both of them coming from the same string x, let's say. We want that it is basically a constant factor approximation to the eddy distance between the corresponding substrings I and j. In particular, it is always lower bounded by eddy distance, and then it is upper bounded by this squiggly inequality. This squiggly inequality means that, first of all, it is up to a constant factor, and two is that it will not always hold, not for any pair ij, but it will hold for pairs ij where it matters. Okay, where it matters is, well, where it matters at the end of the day for computing eddy distance, basically. Okay, it's a formal statement. It's not too hard to kind of make it more formal. It will involve roughly saying, for all possible alignments, something happens kind of, but not to get into too many details for now. Okay, think about this as an approximation to the distance between I and j, and this is one kind of property. The second property is that computing this, answering a query of this data structure takes time, which is n to order epsilon. Okay, and now basically the goal will be to just to show how to do one of these arrows, right? How to, given a data structure for shorter substrings, build a data structure for longer substrings. Okay, and we want that each of the steps takes time, which is nonlinear. Again, n to 1 plus order epsilon. Okay, so this is, this is our, slightly less ripe data structure, and this is a little bit more ripe data structure. This is on shorter substrings, this is on longer substrings, and I want to go from, here to here. There are basically two components. Think about this as like, two stages in a sense, but, there are really two components. You'll see why. Number one is what we call alignment distance oracle. Okay, think about this alignment distance oracle as defining yet another distance, which is also an approximation to a d distance. Okay, but it's really a wraparound around this triangle. As in, it's an algorithm for computing distance between strings of length w now. Okay, so this is, we went, this triangle, the less right triangle is, shorter substrings. This AL is on longer substrings. So this, this thing you will put together substrings to somehow compute distance on longer substrings. But it's a wraparound, right? Because it will use certain time, which is n to the epsilon, but it will also use oracle calls to the data structure itself. Okay, all right. So now, what is the difference between ALW and DW? Okay, so in a sense, obviously we want that this DW is a distance oracle for this distance, this alignment distance. Okay, but alignment distance is basically, it's an algorithm that given two strings outputs what is the distance between them, right? As opposed to DW is a data structure where for any given pair it will output things fast. Okay, put differently. We don't want, in particular, this DW will not will not use oracle calls into the shorter substrings data structure. Okay, I mean, we could, but then, when we put everything together, then, there are too many levels of recursion and we get back, basically quadratic time. Okay, so in some sense, this uses the oracle calls here. So we want, in some sense, to take this and kind of represent it as a fixed distance oracle. Okay, so, and this is done by what is called matching algorithm. So we build this data structure DW from this alignment distance oracle AL. Okay, and it's basically done in two steps, right? The first step is the important one, or where the heavy work goes. We call it matching algorithm. And basically what it does, it takes this ALW distance as an oracle, right? As, given a black box that, has some properties, right? And runs in time, which is, n to the epsilon roughly. And say like, well, I can query any pair of strings I want from it. Then I'll build a graph, GW, which I think about as a metric, as a graph metric. Basically, it is, it's a graph, it's a weighted graph, and you can define shortest path. Its nodes are, again, substrings of x and y. So there are 2n vertices of this graph GW. You can define shortest path on it. And it has the, again, very similar properties, right? That the distance for any two substrings I and j, the distance in this graph is lower bounded by the distance and upper bounded by whatever we want to approximate this alignment distance. And again, up to this squiggly inequality, meaning that it is up to constant factor and where it matters. Okay, so not everywhere, but just enough to be able to compute any distance. Okay, so we build this graph. Okay, and now I guess the experts in the audience will recognize that going from this graph to DW is basically just distance oracle. Okay, data structure, any standard one. I mean, any standard one, but we need like one extra property that makes it slightly less trivial, or immediate to apply any of them. But basically, it's a distance oracle data structure, and what we get, since this is kind of a data science talk, I wanted to mention that one perspective on this DW is that this is a dimension-reduced metric that mimics this alignment, the whatever distance the alignment oracle gives. Okay, so it is conceptually this way, and actually the data structure itself is actually a dimension-reduced set of vectors, and you'll see why. So really, it is okay to use any distance oracle data structure, with the only caveat is that we need that the output of a data structure is a metric, because we'll continue doing this on and on, kind of right in the next iterations. We need to make sure that we approximated the distance by something which is a metric, because then we'll be using again trial and inequality and stuff. We cannot lose metricity. Okay, and unfortunately, things like, let's say, standard distance oracle data structure, let's say Torus-Vig, again, for those of you who have heard about it, will not work because, as far as I know, we are not guaranteed to output a metric. So we use something, I guess, which predates Torus-Vig, but maybe few of you know of. We can actually embed the metric, the shortest path metric defined by this graph GW into an infinity. Okay, of dimension, which is n to the epsilon. So at the end of the day, this data structure itself is just particularly simple data structure where each vector x, in some sense, each substring xi or yj will be an n to the epsilon string of numbers. And when we compute the distance, we just take these two strings of numbers and compute an infinity between them. Okay, so maximum of the absolute value of the differences. Okay. Okay. Any questions so far?
I have a quick question.
Mm-hmm.
So the squiggly upper bounds, like, do they hold for the same pairs of substrings, like when you're going from the lower dimensional or lower length substrings to the upper length substrings, like the dw over and the epsilon to the other distance oracle?
Say that again.
These distance oracles, like when you're building a distance oracle for dw from smaller length substrings, like, do they approximate the edit distance like up to constant factors for the same set of substrings, like same pairs of substrings, or is it like
this is the guarantee, basically, that it is always lower bounded, but it is upper bounded up to a constant factor, but not for all ij, but for ij's that matter.
So I'm hoping it's
sorry.
Yeah. So where it matters is like kind of like, does it change from like, I did not understand
Yes.
what do you mean by
It can change
matters.
from one length to the other. Yeah.
Okay.
I mean, to be precise, where it matters at the end of the day, it's actually on average, right? So if the minimum basically the cost of the minimum alignment of the substrings will be upper bounded by, under DW will be upper bounded by the cost of the minimum alignment under EDW. So to be precise, this squiggly thing and where it matters really means that on average, for the optimal alignment, it is the upper bound holds.
Okay. Okay. Thanks.
Thanks for the question. Okay, so, and let me talk about matching algorithm. This is, where some heavy stuff goes. So, again, let me try to simplify these things as much as I can. So first of all, what do we do? So we have an oracle, ALW, right, which, for every pair of substrings ij tells us whether, it gives the distance between them. And we want to build a graph where the shortest path on this graph approximates this distance ALW for any pair of substrings. Not that we cannot just compute all pairs distances, because there are n squared. Remember that the number of points in the metric is n squared. So, a priori, the information captured by this box could be as large as n squared. So this is why where it matters, this notion of where it matters is almost necessary, because at least assuming that this is a generic metric, right? This is kind of the most we can, in a sense, assume. Otherwise, then just to extract all this information, we would need to ask all possible queries, right? So obviously we're not doing this, right? Because this would take too much time. So we'll do, only where it is necessary in a sense, right? So this is why there is this weird matters kind of caveat. Okay, so we'll build this for one scale only, right? So think about, basically all the distances, the action happens around scale C, let's say. So building this graph, a little bit more specifically or formally, what these properties this graph will have is that if we have an edge in this graph, then this alignment distance, and I'm dropping the subscript W just because it's not important for the rest of the presentation. It's everything will be of fixed length W. Okay, so this means that this will imply that alignment distance between ij is up to constants are bounded by C. And also, and think about this as roughly the notion of where it matters. For any alignment pi, okay, between substrings of x and substrings of y, if a substring xi and its match under this optimal alignment pi, if it is at short distance, this distance, which is itself an approximation to the distance, is upper bounded by C, then will be at most a 2-hop path in G. Basically saying that we really care about 2-hop paths really in G, at most 1 or 2 hop. Okay, and this holds for all I except for a number of y's which is proportional to the error that already exists. Okay, so obviously we won't be able to do this because then there is what does the alignment mean really, right? It's like this would if it were to hold for all possible i's, then that would immediately imply that we managed to preserve the alignment distance for all pairs x versus y. Okay, so the notion of the alignment is that the alignment tells us how much error we can tolerate, right? As in, we'll miss some matches, some of these things will not hold, but the number of them will be proportional to the error that already exists, right? To the number of pairs that are already not a distance less than C. Okay. All right. So this is, this is what we want to do, right? This is the goal. This is kind of the formal goal. And the amount of time that we want to spend is near linear. This is the matching algorithm. We'll do this constant number of times. So we want to spend time, which is near linear time, as well as number of calls to AL. Right? Remember with AL, each call takes something like n to order epsilon time. So we'll still have this runtime at the end of the day. And let me introduce an assumption for the rest, I guess, for the next 5 minutes, which I'll call ultra triangle inequality. And it is, it is equivalent of triangle inequality, but it's just pushing it to the extreme. And in particular, I'll assume that for any pair of substrings ij, either they are very close, namely a distance at most C, or they are very, very far, namely distance more than C. Equivalently, this can be seen as that all our substrings of x and y can be partitioned into equivalence classes. Okay, things that are close between themselves versus, and everything else is far. Okay, and here is an illustration. So now this is, this corresponds to strings x and y, kind of in this picture below. Now, the capital letters correspond to, in a sense, identities of, or the names of the equivalence classes of the substrings that start in that position, right? So this is really a representation of the substrings xi, right? So I call them capital A or C, right? Where they really represent substrings of original x and y. This A, this means that, substring starting here is very close to substring starting here, very close to substring starting here, very close to substring starting here, but, as well as here and so forth, but not to, things like C's or B's or D's and so forth. Okay. This gray stuff corresponds to the optimal alignment, that we care about. The red stuff corresponds to things which are error, right? This substring will match to something which is very far, right? Corresponding to the distance being much more than c. So in some sense, this is an error, and there are kind of two errors. Not everything is shown, kind of, but in some sense there are two errors. So the error, the quantity here, order error, is like order 2 basically. Okay. So the goal now becomes to identify these classes, right? I mean, this would correspond to a graph which is very close to being a clique. Maybe not clique, but a partition into groups where the diameter is 2, right? Partition into connected components where each connected component has diameter 2. This is roughly what we want. We'll not do this perfectly. We'll do some error because of this kind of condition. And I should say that this assumption of ultra triangle inequality is a huge simplification. That probably the amount of work done to kind of go beyond this is more than work done to solve this case. And there is no easy way to reduce to this case, but hopefully it illustrates some ideas from the paper. Okay, so here is the main loop, and yeah, sorry for rushing through this here. Like it's not really the algorithm that we are doing because this is only under this ultra assumption, and but I want to roughly illustrate one idea here, right? So so don't worry necessarily about all the details. I'll highlight the idea. It's really on the next slide. Okay, so the main loop, so here is the case. The main loop will basically say, like, well, we are partitioning IW. Remember, we want kind of this graph. We want to partition things into these basically equivalence classes. So we start with everything being together, and then we begin splitting things apart, kind of, right, corresponding to these equivalence classes. Okay, there will be 1/epsilon steps of refinement. So we start with a partition that has everything, and then the next partition will be some refinement of it, and so forth. Okay. So when we build a partition pi t, it will basically correspond to taking partition pi t plus 1 and splitting each part of it into something like lambda parts, roughly, which is, again, something like n to the epsilon. And how this is done? Well, for each new part in pi t, we sample, we do something as follows. We sample an anchor A. Okay, something like this here. This is an anchor, let's say, right? These letters, which are black or red, are basically the things which are in the current part. And since we're just focusing on one part in the previous partition, we sample some A. Then we compare this anchor, right? This blue anchor, to everything else in the part, right? So we compare to A and C and B's and everything here, and we find it's friends basically, right? It's friends in the same equivalence class. So basically all the other A's here. Okay, some of them are errors, some of them are not. Okay, we call this E of A. This is the equivalence substrings, right? The distance at most C. So what we do is that, well, each anchor will lead to a new partition in the new, a new part in the new partition. Okay, it has some kind of budget of how many substrings it has to capture. Okay, so this is the set of equivalent strings, right? All the other A's. So what we do is that each of these U of A is given certain capacity. But all these, blue or red arrows will go into the same new part because, why? Because, well, we don't know whether this A will match to this A or this A or this other A. We know that all the A's here, if we are to match to the string Y, we need to match to all the set of A's in the other string. So we put them together in one part, but that's not enough usually, as in the part will be too small. Imagine something like B, which is, has just one match of it, right? So that will make to a very small part. So we say like, well, each part, each of these anchor together with its, friends, basically, equivalent substrings, should capture much more of the other substrings, right, to make a new part. So what we'll do is we'll give them some kind of capacity, which basically, target part size divided by the number of them. Right? So together all this entire set of equivalent substrings have to create a part of certain size, ignoring the numbers. So we'll each of them will be responsible for a certain amount, right? To equal amount of things to capture. And what we do, and maybe I'll skip the rest, is that we partition the proximity. So sorry for kind of flashing through this, right? I mean, anyways, this is not super technically not super accurate, but roughly what we'll do is the following. We'll do what we'll call proximal extension. Okay, so each string I in this extension has certain kind of budget, right, of strings to capture. What it says is like, well, I'll distribute it to things around me, right? Literally around me, right? I mean, this is, like strings to the left, strings to the right, right? So I'll distribute. But we will not take this to be the part, right? This will be, I mean, one can think through this, right, and see that this will not work. The amount of error will be too much. So we cannot do this. What we'll do is instead, we'll do something else. So we'll use this partitioning, distribution of the credit or the capacity that each of the strings has. We'll distribute it around neighbors, right? This proximity in this like local community kind of, okay? And what we do is the following. So to construct a new partition, each other string, let's say something like, I don't know, B, for example, right? It will, there is a bunch of these anchors, right? And in some sense, different anchors will compete for the same substrings to capture. So one string, just waits until we've seen all the anchors. Each anchor tells it, how much it wants that J, for example, that substring. Okay, but that basically means that each substring, every possible substring, will have a vector of numbers that corresponds basically to the, how desired it by an anchor and its strength. Okay, and when we do the partitioning, we think about this as weighted set, and we apply min hash basically to assign things to the partition. Okay, and the property that we use of min hash is that probability that Xi and Y will be separated will be roughly the L1 distance between, these vectors of, its desirability by, local anchors kind of. And this will roughly correspond to the local error. So basically to the error around this substrings Xi and Y by A. And overall kind of average of the local error will be roughly equal to the total error. So the expected number of these pairs that are separated will be proportional to the average of local error, which is total error. Okay, this is super high level. There are many more details, how do we choose this neighborhood proximity and so forth, right? And, turns out that, to do this, you put this in an entire loop and you consider different R's and then you have to do certain kind of thresholding of these numbers, just because if you don't, then you get too big parts, right? But again, the basic principle is that a substring is partitioned according to what happens in its neighborhood. Basically, what are the anchors and what is the action that happens around it at within certain radius around it. Okay, going beyond this ultra assumption is hard, just because we can't really reduce to it. Okay. So it is normal, again, kind of, for the experts in kind of, metric decomposition kind of literature, if you've heard things like FRT decomposition, for example, or PADI decompositions, then, I mean, it's kind of, one of the standard things to apply in this kind of scenario, but unfortunately, it doesn't quite work because, there is a constant probability that we all, these kind of partitions will separate the matching pairs, which means that the error after these kind of randomized partitions will be proportional to n, and we lose everything basically. So basically, the main way to kind of go around this is basically to smooth everything out. Okay, and this means that we won't really have partitions, but we'll have continuous versions of partitions, which we'll call coloring. So this means that an interval is partitioned logically among different parts, which we think about colors and so forth. And instead of thinking about, when we're comparing these vectors and we're thinking about kind of using Jacquard, which kind of corresponds to some form of L1 distance between vectors, we use what is called distortion resilient, or what we call distortion resilient L1, which basically says, consider two vectors, compute L1 distance, but only on coordinates which are sufficiently different. Okay, where sufficiently different means up to some polynomial factor. Okay, more details on this element oracle, but I didn't talk at all about. But let me just go to the last slide. Already a few minutes over. So finale is that this is the statement. We can compute constant approximation to the distance in linear time. If you're curious what is the approximation, I wouldn't be. It's horrible. It's at least doubly exponential in 1 over epsilon, about doubly exponential in 1 over epsilon. So obviously, the first natural open question is to get a reasonable dependence on 1 over epsilon. For example, polynomial in 1 over epsilon approximation feels like a very natural goal. This is, this would be doubly exponential improvement over the approximation that we have. And why I'm saying that this is natural is that, in some sense, at least our result, but some previous results as well, use certain techniques which are kind of dimension reduction for generic metrics, right? Things like distance oracles, like the type of trade-offs that maybe for Torub's-Wick type distance oracle, where you get something like 1 over epsilon approximation, and the space complexity or query time complexity goes up by a factor of n by epsilon. Right? So it would be natural to have this kind of trade-offs between for computing at a distance as well. Okay, but also, another way to view it, or to reformulate the question, is to say, well, what is the smallest approximation that we can get in sub-quadratic time? At the moment, the best we know is 3 plus epsilon. We don't know what is the, what can we, what is the best runtime for 3 plus epsilon. Current best is something like n to 1.6. I think that n to 1.5 is natural. I should mention this n to 1.6 is by Goldenberg, Rubinstein, and Saha, Marna, our host. And another question is, can we get below this approximation 3 that, this somehow goes beyond using just triangle inequality? There are some results where in some regimes turns out that you can do this. And of course, can we get constant approximation for many other distance problems that we care about, things like text indexing or nearest neighbor search or metric embeddings? That would be very, very cool if we could do that. Thank you, and sorry for running over.
Thank you, Alex. Very nice talk. Are there questions from in the audience? Like, you can unmute yourselves and ask questions. So I just have one question, like, if it's not really a question about the technical part, it's just if we want to reduce the approximation factor, if we are assuming like the edit distance is really large, like near linear, then can you do better here? Because even the previous papers had doubly exponential approximation factor. No,
not that I know. Yeah. I guess improving the polynomial in 1 over epsilon approximation, I don't know. I mean, yeah, I don't know. Mm-hmm. Even for additive approximation, even when the distance is close to linear NN, yeah. I don't know how. I think these recent results are also doubly exponential in 1 over epsilon. Sorry. Yeah, I know the algorithm was like crystal clear, ready to be implemented tomorrow. I know it's a lot of details. Yeah.
Well, I think we got like good ideas about the different modules. The steps. Yeah.
Cool.
Are there questions from the audience?
Can I ask a question?
Yes, please.
Yeah.
So I can see CDK reference on your last slide. What is this paper?
Oh, it's by Chakraborty, Das, and Koucky. This is a subset of the authors of the Fox 18 best paper, but get constant approximation. What they get is that for text indexing that can get constant factor approximation in time, which is
Sublinear in the length of the text?
well, not sublinear the length. Text indexing meaning it's not data structure. It's you have a text of length, let's say 2n, and you have a substring of length you have a string of length n, and you want to compute the distance to each substring of length n from the text.
It's pattern matching.
Pattern matching. Sorry, maybe I'm using one reference which calls it text indexing. I think it's the survey of Navarro that calls it text indexing.
And for you, is it text indexing or pattern matching?
It's the same problem. It's the offline problem, right? You have a substring of length 2n. A text of length 2n. You have a substring of length n, and you need to compute the edit distance to each substring of the text.
Okay.
And you should see that it is not why these techniques are relatively easy to extend to text indexing is that as already kind of suggested in the talk, the main focus is to compute how many recursive calls do we need to compute for substrings of shorter length. After that, you just run dynamic programming. Now, dynamic programming, once you build this entire graph, computing you can compute more shortest paths, right? You don't once you build the entire kind of approximation to the dynamic programming table, then you can compute shortest paths starting from different positions as well. This is why extending to text indexing is relatively easy.
Yep, thanks very much.
But definitely, it's far from getting similarly strong results.
Can I ask a question?
Yes.
Yeah. So as this question is asked, yeah. So can your algorithm be parallelized? Like we have this independence in all previous algorithms in between windows. That's why we can extend it to pattern matching. So is there this kind of independence in your algorithm as well?
So I'm trying to parse. Can you repeat us again?
In all previous algorithms, when we compute the edit distance among substrings, we have this independence. Like if once you compute first substring of x versus all substrings of y, you can just forget the first substring of x. You don't need to remember it. So in your algorithm, do you also have this kind of independence?
Not sure. Yeah, I'm not sure. Sorry, I'm not fully understanding the question. I'm sorry. There are times where we need to look at the entire set of strings and let's say compute a graph on it, right? And then compute a metric embedding of it, for example. So that requires looking at the entire thing and the entire graph, for example.
Okay. Okay. Thank you. Yeah.
Any other questions? Otherwise, let's thank GV. Do you have a question?
No, not quite. Like I was just wondering, like, would you know, like this might also be to some of the audience members, like what is the state of the art in the sublinear models, like in the streaming or the property testing kind of models? for computing the edit distance or approximating the edit distance.
I think Barna is the expert. Actually,
So I did some work on the sublinear model. So in the sublinear model, like still we do not know the results, the kind of results that we have. Like we have the gap version of edit distance where we can distinguish between whether edit distance is k or below k or k to the power, say 1 plus epsilon. But we still do not have any algorithm that can distinguish, say, k versus constant times k in the sublinear region.
Okay, thanks.